Every time a hurricane tears through a city, thousands of windows stare it down and win. That shouldn't be possible. Glass is brittle, storms are brutal, and yet the skyline stands. The answer has less to do with the glass itself than with what we've learned to do to it. The secret starts before the glass ever reaches a building. Modern architectural glass isn't the same material as a drinking glass or a window pane from a century ago. It goes through a process called tempering, where sheets of glass are heated to over 600 degrees Celsius and then blasted with cold air. This rapid cooling compresses the outer surfaces while the interior stays in tension, creating a kind of internal tug-of-war locked permanently inside the material. The result is glass that's 4 to 5 times stronger than it was before. And when it does finally break, it crumbles into small, blunt pebbles instead of long, knife-like shards. But tempering alone doesn't explain how a glass curtain wall survives 150-mile-per-hour winds. That comes down to lamination. Most storm-rated glass is actually 2 or more panes bonded together with a thin plastic interlayer, usually polyvinyl butyl, or PVB. If the glass breaks, the interlayer holds every fragment in place. The window may crack, it may look destroyed, but it stays in the frame. The building envelope stays sealed. Rain, wind, and debris stay outside. This matters more than it sounds. In a hurricane, it's rarely the wind itself.
And the glass is only half the story. Even the strongest pane will fail if what's holding it isn't up to the job. The frame, the sealant, the anchoring system, every connection between the glass and the building has to absorb and redirect the same forces trying to tear it apart. Engineers call this the curtain wall system. And in a modern skyscraper, it's one of the most precisely engineered assemblies in the entire structure. The curtain wall doesn't just hold glass, it flexes. This is the part that surprises most people. Tall buildings in high winds don't stand rigid, they sway. A skyscraper in a major storm can move several feet at the top. If the glass panels were fixed in place like tiles on a bathroom wall, that movement would crack them within minutes. Instead, each panel is mounted with deliberate tolerance, small gaps, rubber gaskets, and floating anchors that let the glass shift independently of the building's movement. The frame moves, the glass moves with it, but on its own terms. It's the same principle that keeps bridges from snapping. Controlled flexibility beats rigid resistance every time. Then there's the shape of the building itself. Glass towers aren't designed in a vacuum. Wind engineers run simulations and physical scale models in pressure tunnels for months before a single beam is placed. They're looking for how wind wraps around corners, where pressure spikes, where turbulence concentrates. A slight curve in a facade, a tapered floor plan, a chamfered edge. These aren't just architectural choices. They're aerodynamic ones. Some of the most recognizable skylines in the world were shaped as much by wind as by any human designer. Nature, it turns out, has been the most demanding client all along. But none of this knowledge came free. The engineering standards that protect glass buildings today were written in large part by disaster, by the buildings that didn't hold, by the storms that exposed every shortcut, every underestimation, every assumption engineers had made about what wind could do. Hurricane Andrew in 1992 caused over $27 billion in damage across South Florida, much of it because buildings that should have held simply didn't. Investigations afterward found widespread failures, not in the glass itself, but in the installation. Improper sealants, frames anchored with the wrong fasteners, curtain wall systems that had never been tested to the standards they claimed to meet. The storm didn't just destroy buildings, it exposed an industry that had been cutting corners in places no one could see.